Before the first winds howl, before the first clouds gather, the ocean already knows. In the deep blue, long before a hurricane takes shape, the sea begins to shift. And those who listen, really listen, can sense it. Sea surface temperatures begin to rise, not just at the top, but dozens of meters below. Ocean heat content surges, currents twist, the salinity balance changes, and all of it happens in silence. Before Hurricane Ian struck in 2022, satellites recorded a massive warm pool forming off the Yucatan. That energy wasn't just passive heat, it was fuel, waiting for something to ignite it. That's what hurricanes do. They don't create chaos from nothing. They draw from the ocean's energy, 1 degree at a time. And often, the most powerful storms start in the quietest waters. In this series, we uncover what the sea tells us, before radar, before rain. Because nature whispers before it screams. And the ocean? It always speaks first. If you want to understand how hurricanes are born, you don't start with the sky, you start with the sea. The ocean doesn't just hold water, it holds energy. And in the days, weeks, and sometimes even months before a major hurricane, that energy builds silently beneath the surface. Sea surface temperature, SST, the spark beneath the storm. Hurricanes require warm water to form, specifically temperatures above 26.5 degrees Celsius in the upper layer of the ocean. But more important than surface warmth alone is something called ocean heat content, OHC. This measures how deeply that warmth extends into the water column. Why does this matter? Because when a hurricane stirs the ocean, it brings cooler water from below to the surface. If that deeper water is also warm, what scientists call a deep warm layer, then the storm doesn't weaken. In fact, it can rapidly intensify, pulling more and more energy upward. This is exactly what happened before Hurricane Laura 2020 and Hurricane Ian 2022. In both cases, satellite readings showed anomalously high ocean heat content in the Gulf of Mexico days before either storm formed. Those readings weren't just numbers, they were warnings. Open quote, NOAA's data showed the Gulf's heat content reaching record levels just 72 hours before Laura strengthened from Category 1 to Category 4 in less than 36 hours. Close quote. The ocean gave us the clue. We just had to be paying attention. Ocean currents and loop currents, the invisible conveyor belts. Another silent signal from the sea comes from its currents, especially the loop current in the Gulf of Mexico. This warm, fast-moving stream flows northward from the Caribbean, curls around the Gulf, then exits through the Florida Strait. When hurricanes pass over the loop current or its eddies, spinning offshoots, they often undergo explosive strengthening. Why? Because these currents bring up deep reserves of warm water, not just surface heat, but columns of warmth that extend 100 meters or more. In 2005, Hurricane Katrina crossed a loop current eddy just before reaching New Orleans. Its central pressure dropped sharply and wind speeds increased dramatically, transforming it into a monster. Similarly, Hurricane Ida 2021 intensified rapidly after tapping into the loop current just south of Louisiana. The ocean's conveyor belts moved the fuel into place. The storm only had to follow it. Salinity, thermoclines, and the quiet chemistry of storm formation, beyond temperature and currents, ocean scientists also look at salinity and thermoclines, the boundary layers between warm surface water and colder deep water. Changes in salinity, especially in estuaries or coastal zones, can indicate higher evaporation rates or the presence of warm, nutrient-rich runoff, both of which can alter how a storm forms or moves. Thermoclines, on the other hand, act like speed bumps or accelerators for vertical mixing. If the thermocline is deep and weak, the storm can tap into more heat. If it's shallow and strong, it might block some intensification. These oceanic subtleties are being tracked more and more by autonomous buoys, Argo floats, and remote sensing satellites, providing scientists with a better picture of how the ocean prepares for a storm, long before the clouds appear. How satellites see what humans can't. Thanks to advances in satellite technology, we now have near real-time monitoring of SST, OHC, current velocity, and salinity. NOAA's GOES East and JASON 3 satellites detect surface changes in heat. Argo floats relay temperature profiles from deep layers of the ocean every 10 days. NASA's GRACE-4 even tracks subtle gravitational anomalies caused by heat expansion in ocean masses. These tools allow meteorologists to anticipate hurricane potential even before a storm forms. When ocean heat and structure are right, forecasters know to raise the alarm early, yet public awareness of these signals remains low. Most people associate hurricanes with the sky, not the sea. But the truth is, by the time the sky speaks, the ocean has already shouted. In the next section, we'll explore how the atmosphere responds to the ocean's energy and how changes in pressure, moisture, and upper-level wind create the conditions where tropical storms come to life. Because the sea may spark the storm, but the atmosphere decides whether it survives. Before the hurricane forms, the pressure falls, not in sudden gusts, but in subtle shifts. You can't see it and you can't feel it, but the atmosphere is changing. Barometers begin to dip. Slowly at first, then faster. This drop in pressure, often hundreds of miles from land, is one of the earliest signs that a storm is organizing. Before Hurricane Ida strengthened in 2021, meteorologists noted a steep drop in surface pressure over the Gulf. That signal came nearly 36 hours before the storm reached Category 4. This isn't just a coincidence, it's physics. As pressure falls, air begins to rise. Rising air cools and condenses, releasing latent heat. That heat makes more air rise, forming a powerful feedback loop. It's not the clouds that form first, it's the vacuum, an invisible, spinning space of instability. And sometimes, long before the storm is named or even noticed by the public, the pressure has already begun its quiet collapse. In this chapter, we uncover how the atmosphere prepares the stage for the storm to grow. Because before the winds roar, the air falls silent and lighter. In meteorology, one of the most critical and most overlooked clues that a hurricane is forming is a drop in atmospheric pressure. But what does that actually mean? The physics of falling pressure. Atmospheric pressure is simply the weight of the air above you. At sea level, the standard is 10,013.25 millibar. When a tropical disturbance begins to form, it's often accompanied by a slow but steady pressure drop, sometimes just a few millibars at first. This drop is caused by rising warm air. As surface air warms, usually over heated ocean waters, it becomes less dense and begins to rise. As it rises, it leaves behind a zone of lower pressure at the surface. Air from surrounding areas rushes in to fill the gap, which also warms and rises, reinforcing the cycle. Eventually, if environmental conditions are right, this becomes a low-pressure system, the embryonic stage of a tropical storm. And once the pressure drops below 1,000 millibars and continues falling rapidly, forecasters know a hurricane is likely forming. Key atmospheric signs of pre-storm activity. There are several measurable atmospheric changes that accompany or precede a hurricane's development, including 1. Rapid pressure drop. A pressure drop of 1 to 2 millibars per hour is considered a red flag. In Hurricane Michael 2018, pressure dropped 39 millibars in just 24 hours before landfall. 2. High mid-level moisture. Water vapor imagery often shows a moist core forming at 500 to 700 millibars levels. This enhances vertical convection, rising air that forms cloud towers. 3. Decreasing wind shear. For a storm to grow, it needs light upper-level winds. Wind shear disrupts storm organization. When it falls, storms can rapidly align and strengthen. 4. Vorticity increase, a measure of spin in the atmosphere. When low-level vorticity increases, cyclonic circulation becomes more defined. 5. Low-level convergence, upper-level divergence. Air piles up at the surface and is vented away aloft, enhancing upward motion. These conditions together create a vertical engine that can pull moisture and energy from the ocean and release it into the sky. How forecasters use pressure drops to predict intensification. Modern meteorologists track pressure using reconnaissance aircraft, NOAA's hurricane hunters, that drop sensors into developing storms. Buoys and automated ocean stations that measure pressure in remote zones. Satellite-based algorithms like the Dvorak technique that estimate intensity based on cloud patterns and temperature gradients. When all of these tools show falling pressure, especially when paired with rising sea surface temperatures, it's a strong indicator that rapid intensification is possible. In the case of Hurricane Ida, pressure dropped from 995 millibars to 29 millibars in 36 hours. That pressure drop was the engine of intensification, and it was measurable long before the storm turned deadly. Why pressure isn't felt by the public, and why that's dangerous. Unlike rain or wind, pressure is invisible. You can't feel it drop unless you're very sensitive. Some people experience headaches or joint pain. That makes it an easy warning to ignore unless you're actively monitoring data. This disconnect between perception and reality is part of what makes hurricanes so deadly. The pressure drop signals danger, but unless it's translated into a warning people understand, it's often missed. That's why the National Hurricane Center now issues rapid intensification risk notifications when certain pressure and heat thresholds are crossed, even if the storm still looks small or disorganized. Because by the time the storm looks dangerous, the pressure has already done its job. Case study: the silent collapse before Hurricane Wilma. Hurricane Wilma holds the record for the lowest central pressure ever recorded in the Atlantic, 882 millibars. But 48 hours earlier, it was just a tropical storm. Meteorologists were shocked when aircraft sensors detected a pressure drop of 97 millibars in 2 days. That collapse allowed the storm to explosively deepen, gaining energy at a rate almost never seen before. The sky still seemed relatively calm in parts of the Caribbean, but the air, measured, not felt, was already spinning violently. As we've now seen, the ocean feeds the storm, but it's the air that builds its core. In the next chapter, we turn to the wind, how its shifts, stillness, and strange patterns tell us even more about what's coming. Because wind is not just movement, it's information. The wind is nature's voice, but before a hurricane, it goes quiet. Not because the danger is gone, but because it's just beginning. In the hours or even days before a storm forms, surface winds in the tropics may drop off. What once felt like a steady breeze becomes an eerie stillness. For those who've lived through hurricanes, this quiet is unforgettable. It's not peace, it's pressure being pulled upward. As warm air rises to form the storm's early core, it draws wind from below. That pull reduces surface wind, creating the false impression that things are calming down. But in reality, the atmosphere is preparing for violent rotation. Before Hurricane Katrina intensified in 2005, many parts of the Gulf Coast experienced long stretches of near-total calm. Fishermen called it dead air. Forecasters saw it as a warning. Even birds flew lower. Insects disappeared. These small shifts, quiet winds, strange patterns, wildlife acting differently, are not random. They are nature aligning for release. Because when the wind slows, that's sometimes the loudest message of all. When people think of hurricanes, they think of powerful winds, walls of air that tear through trees, buildings, and coastlines. But what's less known is that long before those violent winds arrive, something much quieter begins to unfold. An eerie, sometimes total stillness. This calm is not a coincidence. It's a scientifically documented stage in the life cycle of many tropical cyclones, why the wind slows down before the storm. In the early stages of storm development, warm, moist air begins to rise from the ocean surface. As this air ascends, it creates low pressure at the surface, drawing in air from the surrounding region. But if that rising air becomes highly organized, it starts pulling more vertically than horizontally. This vertical ascent leads to reduced surface wind speeds, suppressed horizontal turbulence, a sense of dead air at sea level. This phenomenon is common near the center of developing storms, particularly near what will become the eye of a mature hurricane. In meteorology, this is known as the subsidence zone, a ring of descending air that surrounds the storm's eye wall. Even in the formative stages, this structure can suppress wind and noise. Evidence from past storms. In Hurricane Dorian, 2019, NOAA buoys detected significant drops in surface wind speed 18 hours before the storm reached Category 5 intensity. At the same time, upper-level winds increased and spiraled inward, indicating the storm's vertical structure was tightening. During Hurricane Harvey, 2017, weather stations in the Gulf showed nearly zero wind gusts for up to 6 hours as the eye approached. Many residents, seeing calm trees and smooth water, assumed the storm had shifted away. It hadn't, it was building strength. This false calm has caused tragedy before. People who misinterpret stillness as safety may cancel evacuations or delay storm prep. By the time the outer rain bands arrive, it's too late. Wind shear, a hidden player. Not all wind is at the surface. One of the most important factors in storm development is wind shear, the difference in wind speed and direction between the surface and the upper atmosphere. Low shear allows warm air to rise vertically, supporting storm formation. High shear disrupts organization and can tear apart developing systems. Before a hurricane strengthens, a key shift is the reduction of wind shear, especially in the 5,000 to 15,000 feet altitude range. This quieting of vertical turbulence is not visible to the naked eye, but it shows up in models and soundings. When wind shear drops suddenly and ocean conditions are favorable, rapid intensification becomes likely. This makes quiet surface winds a dangerous double signal: no motion below and smooth flow above. Animals react to subtle wind changes. Interestingly, wildlife can often detect these wind shifts better than humans. Birds are especially sensitive to barometric pressure and wind pressure gradients. Before several major hurricanes like Irma, Maria, and Katrina, bird migration paths were altered, with many species flying low or in unusual patterns. Insects, too, respond to changes in wind fields. A sudden absence of mosquitoes or flying bugs has been reported hours before landfall in multiple regions. While not a predictive tool on their own, these behaviors match what physics already tells us: the environment begins to shift well before the first gust. The calm is not the end, it's the center. One of the greatest misunderstandings about wind and hurricanes is the idea that calm air means the storm has passed. In reality, if you're experiencing sudden silence after extreme wind, you may be entering the eye of the storm. The eye can be deceptively peaceful: clear skies, no wind, birdsong even. But that peace is temporary and deadly if misread. The eye wall, often the most destructive part of the storm, returns from the opposite direction within 15 to 45 minutes. That's why meteorologists emphasize, open quote, "If winds suddenly stop, do not go outside." Close quote, because in the world of hurricanes, calm is often just the middle. In the next section, we'll explore what the clouds can tell us, how their shape, motion, and even their disappearance reveal the storm's presence before it's fully born. Because nature doesn't just move, it forms patterns, and in those patterns are warnings. Before the storm speaks in thunder, it whispers in the sky. The clouds rise, then freeze. The light dims, not from rain, but from something unseen. That's what many witnessed before Hurricane Idalia struck the Gulf Coast. Days earlier, high cirrus clouds fanned across the sky like warning flags. They didn't move fast, they hovered, and something about the sky just felt wrong. This isn't folklore, it's physics. As a hurricane begins to form far out to sea, it pushes moisture upward into the atmosphere. That moisture cools and spreads, creating streaks of thin, icy clouds far ahead of the actual storm. They're called outflow cirrus, and they're often the first visual clue that a major system is organizing. Soon after, altostratus clouds appear. They block sunlight, the air gets heavy, sunsets lose their color, even birds seem to hesitate. In the sky, movement slows. In your gut, something stirs. Meteorologists can explain this with satellite data and moisture loops. But for ordinary people, it's visual memory. I knew something was coming. The sky told me. We just have to remember how to listen. When we talk about the ocean's role in hurricanes, we often overlook the canvas stretched above it, the sky. Yet the atmosphere gives us some of the earliest and clearest warnings, long before a drop of rain falls. The key is knowing what to look for. High cirrus clouds, the first threads, wispy cirrus clouds that stretch across the sky, are often the first signs of a distant storm's outflow. These clouds form at very high altitudes, over 20,000 feet, and are made of ice crystals. When a hurricane strengthens, it pushes warm, moist air upward. That air cools at high altitude and spreads laterally, forming wide veils of cirrus. To the human eye, these can look like feathered streaks, mare's tails, or even jet contrails frozen in time. Unlike normal cloud movement, they often appear to hang motionless or move slowly in an unnatural direction. Fishermen, pilots, and farmers have relied on cirrus patterns for centuries. In many coastal communities, the sudden appearance of these clouds triggers quiet preparations. Mid-level changes, altostratus, and color shift. As the storm draws nearer, mid-level clouds like altostratus begin to move in. These create flat grey blankets across the sky. They don't bring rain right away, but they filter light in strange ways. Shadows disappear, the sun dims, everything takes on a pale or grey-blue tint. These changes are caused by both the increased moisture content in the atmosphere and the scattering of light by cloud particles. It can feel surreal, even without wind or rain. Photographers often describe this light as milky or unclean. Meteorologists see it as a sign that deep atmospheric layering is taking place, a prelude to heavy weather. The anvil, a towering signpost. In the most intense storm systems, one of the most visible features is the anvil cloud. These are flat-topped thunderstorm towers that expand outward like a mushroom. You might see one on the horizon long before the storm hits. Anvil clouds indicate that the storm has reached the top of the troposphere and is now venting energy sideways. This is a sign of a strong, vertically developed system, usually associated with tropical cyclones and supercells. When the sky stops shifting and an enormous flat cloud appears to sit in one spot, something powerful is organizing. Color warnings and sunsets. Before hurricanes, the color of the sky can change in ways that seem unnatural. Pale yellow or greenish tints in the late afternoon, pinkish haze or dull orange sunsets, washed out blue in midday skies. These colors are caused by a combination of high humidity, upper-level ice crystals and suspended particles, all stirred by distant storm dynamics. While these hues are not unique to hurricanes, their persistence over days in combination with other signs, like stillness or animal silence, increases their meaning. Wildlife and sky changes. It's not just humans who notice. Birds, insects, and even livestock react to changes in light and pressure. Before major hurricanes, it's been widely observed that birds stop chirping or flying, insects vanish, chickens and livestock act restless or retreat indoors. These are responses to barometric drops, but also to light spectrum changes that we often overlook. There are NOAA case studies in the southeastern US where animal behavior matched satellite detections of moisture plumes 2 full days before any public alerts. Satellites and modern tools. Today, we use satellites like GOES East and GOES West to observe outflow cirrus, moisture spirals, anvil tops, and cloud top temperatures. These tools let meteorologists see what the sky is saying before radar can pick up a storm. For instance, cold cloud top temperatures measured by infrared sensors signal that a cloud is very high, often tied to powerful convection. But even with this tech, visual observation still matters, especially in places with limited radar access. The risk of misreading the sky. One danger is misinterpreting the visual calm before the storm as an all clear. That's why education matters. People may look at a beautiful sunset, still trees and strange clouds, and assume it means the storm passed. But it might just mean the storm hasn't arrived yet, or that you're in the eye. In Hurricane Michael, dozens of residents in Panama City saw blue sky as the eye passed overhead. Some went outside to check on damage. They didn't survive the return of the eye wall. Understanding the sky means understanding timing. The sky doesn't lie, it just speaks in patterns. Closing for part 4, the sky gives us signs, sometimes poetic, sometimes scientific, but always there, waiting to be read. In the next chapter, we'll explore what happens when all sound disappears, because after the sky whispers, sometimes everything falls silent. There is a moment before impact when the wind dies, the sky stills, and everything goes quiet. It's not safety, it's not peace, it's pressure collapsing. Survivors of Hurricane Idalia, Katrina, and Michael described the same thing. An eerie hush that swept through just before landfall. The birds stopped, the trees stopped, even the air felt heavy as if holding its breath. This silence happens when the outer storm bands pause and the eye nears. Atmospheric pressure drops rapidly, the wind loses momentum temporarily. This stillness can last minutes. It fools people into thinking the worst is over or hasn't started. But then, without warning, the winds return, harder, colder, faster, and the storm finishes what it began. The quiet wasn't your reprieve, it was your final warning. When the world goes still, move fast. The deadliest quiet before a hurricane unleashes its fury, there is often a moment that deceives even the most experienced coastal residents, a sudden and total silence. This silence is not symbolic. It is not just the absence of noise. It is the physical result of rapid environmental changes as the storm nears peak intensity. Understanding this silence, its cause, danger, and history, can save lives. Meteorological anatomy of silence. As a hurricane approaches, it undergoes cycles of convective bursts and wind band rotations. These are marked by pulses of rain and gusts, followed by brief, calm periods. However, when the storm center, especially the eye or the center of lowest pressure, gets close, a larger stillness can occur. Meteorologists call it the eye lull or pre-eye lull. It is a measurable drop in wind and atmospheric movement that occurs just before the full eye wall strikes. In hurricanes like Katrina and Irma, this phase lasted anywhere from 2 to 20 minutes, depending on the storm's forward speed and structure. Barometric collapse. As the storm's pressure plummets, often to values below 950 millibars, the gradient between the storm center and surrounding air tightens. This compression creates a momentary pause in the flow of wind as the system rebalances itself. To humans, this feels like a heavy atmosphere, thicker air, difficulty breathing, pressure in the ears, similar to rapid altitude change. For meteorologists, it's a key signal. For the public, it can be deadly if misread. Psychological deception. One of the most dangerous aspects of this silence is false interpretation. People often think, it's over, we were lucky, it's passing us by. This pause can lead to people leaving shelters, driving, or even returning home to check on property. But the lull is often followed by the most violent part of the storm, the backside of the eye wall, where winds can be more intense due to directional momentum. During Hurricane Charlie 2004, dozens of Floridians were caught in the open during the eye's passage. Many suffered serious injuries when the back half hit minutes later. Wildlife and environmental cues. The quiet doesn't fool animals. Before the silence, dogs often hide. Birds vanish. Frogs stop calling. Even insects, especially bees, return to hives prematurely. Ants cluster on high surfaces. Horses refuse to graze. Farmers in coastal Louisiana and the Carolinas have passed down this knowledge for generations. These behavioral changes match real atmospheric pressure sensors. In some rural villages, people rely more on what the animals do than what the news says. Historic storm silence. Accounts from historic hurricanes often include chilling descriptions of this moment. Hurricane Camille, 1969. Survivors recall the world stopping for 5 minutes before the wind began to howl. Hurricane Andrew, 1992. Families in Homestead, FL reported absolute silence followed by a sudden wall of debris-laden wind. Typhoon Haiyan, 2013. In Tacloban, Philippines, many residents stepped outside after silence, only to be swept away by storm surge moments later. This stillness is so consistent that it's now taught in hurricane awareness programs worldwide as a red flag, not a comfort. Eye versus edge silence. It's important to distinguish between silence from the eye and silence from edge lull. Eye silence, circular, calm, often has blue sky above. Edge silence, opaque clouds remain, air goes heavy, wind drops, but no visual clearing. Both are dangerous, but the latter is harder to detect and more likely to fool people because it comes before they expect the storm to start. Satellite confirmation. Modern satellites can now observe the exact moment a storm undergoes wind collapse. GOES satellite loops show this as a pause in outer band activity, moments before the central eye accelerates inland. Radar also detects temporary loss of reflectivity in low bands. These quiet zones are the inhalation before the exhalation. NOAA Storm Chaser data confirms that pressure drops as much as 30 millibars in under an hour before major landfall, creating the eerie calm. Communicating the silence. Public messaging often struggles to address this. Weather alerts may say landfall imminent, but few say, if it gets quiet, do not go outside. Emergency response agencies are now revising protocols to warn explicitly about deceptive calm conditions. FEMA's updated hurricane preparedness bulletins include "Don't misread silence" as a core point. Still, local experience matters. In coastal Mississippi, some residents now teach children, if it goes still, it's about to get bad. Final warning. Silence is powerful because it is rare in nature. We're wired to notice sound, but also its absence. When the wind stops, when the sky doesn't move, when even the animals hide, that's when you must act, not relax. Because silence isn't absence. It's pressure, it's warning, it's the final breath before the strike. And those who wait to hear the storm's roar may never get the chance. The hurricane is gone. The sea is still again, but not in the same way. This stillness carries loss, wreckage, and questions. Along the Gulf Coast, silence has returned, but not the peaceful kind. This one echoes through shattered windows, broken levees, flooded streets, and the hollow sound of absence. Now, the question remains, did we listen? All storms have a beginning, but the most important part is the one we rarely see, the signals before the storm speaks. Throughout this series, we've uncovered 5 invisible messengers, 5 early warnings that came from nature itself, and each one, if recognized, could mean the difference between survival and tragedy. The ocean warned us first, not with rage, but with heat. It stored energy, slowly, quietly, feeding itself for months. That heat lifted into the sky like a secret breath. Then came the drop. Pressure fell, invisibly. Barometers dipped like a heartbeat in distress. For those watching, it was the first data point. For those not watching, it was silence. The wind shifted, then disappeared. An unnatural calm, the calm we call peaceful, but which is anything but. It's the breath before the scream. Then the sky joined in. It changed colors. It painted the storm before it arrived. Mute yellows, grey-tinged pinks, and clouds that seemed frozen in thought. Even if we didn't know how to read it, nature wrote us a message. And finally, the world went still. No birds, no insects, no wind, just pressure and a pulse we could not feel. That final hush wasn't safety, it was countdown. Together, these 5 signals create a language, one spoken not in words, but in atmosphere, light, pressure, and instinct. And yet, we forget. We rely on sirens, on phone alerts, on someone else to tell us when it's time to move. But nature never stops speaking. Why we missed the warnings. Some will say we didn't know. Others will say the warnings came too late. But often the signs were there, weeks before landfall. The problem is not silence. The problem is that we no longer know how to interpret that silence. In many indigenous communities, Pacific Islanders, Gulf Coast tribes, Andean mountain farmers, storm signs are part of everyday knowledge. They read the shape of waves, the tilt of the wind, the migration of fish, and the way leaves turn inward before rainfall. To them, disaster doesn't arrive suddenly. It speaks in a slow, rising voice. But in urban societies, we are taught to wait for notifications. And when they don't come fast enough, or when nature behaves differently, we call it unpredictable. Yet it's not unpredictable, it's just unread. What science shows. Modern science is now confirming what traditional knowledge has always suspected. Heat anomalies in ocean surfaces can be detected weeks before a hurricane develops. Drops in air pressure and moisture spirals show up in satellite data up to 10 days in advance. Bird migration patterns shift 24 to 48 hours before a storm, even when humans detect nothing. Sea level pressures correlate with specific cloud formation patterns before cyclone rotation begins. If we merge this data with on-the-ground observation, the result is stronger, earlier warnings. But we have to trust more than just technology. We must rebuild our sensitivity to the natural cues we were born to perceive. The role of education. The most powerful tool against disaster is not concrete levees or billion-dollar satellites. It is awareness. If every student learned how to read a sky, how to interpret a wind shift, how to recognize false silence, evacuation decisions would be made faster, smarter, and more confidently. We don't need to replace radar. We need to restore respect for the natural warning systems already around us. In Japan, schools teach children to recognize earthquake signs, from the behavior of animals to the way certain trees shake before others. In parts of India, tsunami drills include sky observation. In the US, we've begun to teach hurricane categories, but not hurricane cues. That's a gap we must close. What the ocean will do next. Even now, while one storm fades, the next one is already forming. The Atlantic is warming. The pressure maps are shifting. Wind shear patterns are relaxing. Somewhere, the ocean is inhaling again. It will hold that breath for weeks until it releases it as a new name, a new spiral, a new threat. But next time, we can be ready, not just with sandbags or forecasts, but with understanding. The call of Crisis Lens. At Crisis Lens, we believe in reading the invisible. Our goal is not just to report damage, but to uncover patterns, to highlight signs, and to connect science with instinct. Because disasters don't happen in silence. They just begin in it. Every frame we showed you in this series, every still cloud, every falling barometer, every quiet ocean, was a message from the Earth. And our role is to translate those messages for everyone watching. Not to scare you, to equip you. So the next time the wind disappears or the sky turns strange or the birds fall silent, you won't freeze, you'll move. Because now you know. Thank you for watching this video. If you found it insightful, informative, or essential, please consider subscribing to Crisis Lens. We'll continue decoding nature's hidden signals one storm at a time. Your support helps us keep investigating what others overlook. Stay safe, stay informed, stay listening.